want to say a little bit about continuity and questions you might see regarding continuity. So first, let's talk about types of functions that are continuous. So polynomials are continuous on minus infinity to infinity. So we love polynomials. So polynomials are continuous everywhere. So they're our favorites. So rational functions are continuous. Turn that off. Are continuous everywhere on their domain. So what does that mean? So first of all, what's a rational function? A rational function is p of x over q of x, where p of x and q of x are polynomials. So what does it mean they're continuous everywhere on their domain? Well, you have to say what's not in their domain. So where q of x equals 0, let's see, so the domain, we'll write it like this: domain is all reals except where q of x equals 0. So that means a rational function will be continuous everywhere in its domain. So where is it not continuous? At places that aren't in its domain, which would be places where the denominator equals 0. So for example, where is x squared plus 3x over x squared minus 2x minus see 24 continuous? So let's find out what is not in its domain. So x squared minus 2x minus 24 equals 0. So we need to factor that. No number out in front. Good. That makes it easier. Two numbers that multiply together to give 24. Negative 24 add together to give negative 2. That'd be negative 6 and positive 4. And so x equals 6. X equals negative 4. These are numbers that are not in its domain. Not in domain. So if we think about a number line, negative 4 and 6. Open circle there, open circle there. So it's continuous on negative infinity to negative 4, union negative 4 to 6, union 6 to infinity. Okay, so what else? Square root functions. I have x plus 6. That's continuous. The calculus book that's used in 1550 would define this as being continuous at negative 6. I think that's kind of strange. to define it to be continuous at an endpoint, but regardless, I can tell you that it is not continuous for x less than -6, that's for sure, because you can't take the square root of a negative number, and if we're talking about real numbers here, and so you would exclude those. So again, I find it odd that you would include the endpoint, but your textbook does. So it's continuous on -6 to infinity. Now, what if I had 1 over the square root of x plus 6? Now I cannot include -6, because -6 would make the denominator equal to 0. And so our domain, which is also where it's continuous, is -6 to infinity, not including -6. So let's say we had something that looked like this. Let's say we had a question that looked like this. Okay, so, and discuss the continuity. That's kind of very broad, but I'm going to give you all the details that you would need depending on what kind of question was actually asked. So the first thing is we find out what is not in its domain. So we take x squared minus 5x plus 6 equals 0, x minus 3, x minus 2 equals 0, x equals 3, x equals 2. Those would make the denominator equal to 0. So we know it's continuous on negative infinity to 2, union 2 to 3, union 3 to infinity. Now, what types of discontinuities are these? Because you might be asked that. To figure that out, I have to completely factor this and see whether or not my factors cancel or not. So this is equal to x plus 3, x minus 3 over x minus 2, x minus 3. The x minus 3's cancel. That means that x equals 3 is a removable discontinuity. So if you factor it and cancel it out, that's a removable discontinuity. X equals 2 does not cancel out, so it is an infinite discontinuity. As a matter of fact, and it might be asked another question to find the vertical asymptotes, the line x equals 2 is a vertical asymptote. Now, we said it's an infinite discontinuity. If we needed to know a little bit more about it, we would want to find out about the limit as x approaches 2 from the left of x plus 3 over x minus 2, and the limit as x approaches 2 from the right of x plus 3 over x minus 2. So as I approach, if I just plug in 2, I get 0 in the denominator, and I get 5 in the numerator. Whenever you get a number in the numerator and a 0 in the denominator, that means the limit is either plus or minus infinity. So you have to figure out which one it is. So 2 from the left means I'm plugging in a number that's slightly smaller than 2. So a number slightly smaller than 2 makes the numerator positive and the denominator negative. So if I am to the left of 2, I have a positive over a negative, which is negative, which means this limit is negative infinity. If I plug in a number slightly bigger than 2, something bigger than 2 plus 3 is positive. Something bigger than 2 minus 2 is also positive. Positive over a positive is a positive, so that's a positive infinity. So what that means is on my graph, at x equals 2, I have a vertical asymptote. And as I approach 2 from the left, I'm going to negative infinity, and 2 from the right, I'm going to positive infinity. What actually happens at 3? So at 3, if I take the limit as x approaches 3 of x plus 3 over x minus 2, after I've canceled out the terms that would make the denominator equal to 0, I get 6 over 1, which is 6. So that means it approaches 6. So that means I have a removable discontinuity at 3, 6 is a removable discontinuity. And a removable discontinuity looks like just a hole in the graph. 2, 3, 4, 5, 6. So it'd be right here. And we know it's going up like that. Now, if we look at our original function, x squared minus 9 over x squared minus 5x plus 6, we can see the limit as x approaches plus or minus infinity is going to be 1 over 1, which is just 1. So I have a horizontal asymptote at 1. And so it's going to look like that. And look like that. You don't have to know how to draw this graph yet. I was just letting you know. That's for the future. You do have to know how to find the horizontal and vertical asymptotes. So the horizontal asymptote is y equals 1, and the vertical asymptote was x equals 2. Okay, last thing for this video is if you have a question that says something like this, so show that it's continuous at x equals 1. Whenever you have to show that something is continuous, if this is your instructions, then you have to find the limit as x approaches 1 of f of x. And the reason it's 1 is because I'm trying to find where it's continuous there. You have to find f of 1, and then you have to show that those two are equal. Usually, this means you have to find the limit as x approaches 1 from the left of f of x, and the limit as x approaches 1 from the right of f of x. So in this particular example, the limit as x approaches 1 from the left of f of x equals the limit as x approaches 1 from the left of x minus 1, which is 1 minus 1 equals 0. The limit as x approaches 1 from the right of f of x is the limit as x approaches 1 from the right of x squared minus x, which is 1 squared minus 1, which is 0. And f of 1 is, I'll plug into the bottom one because that's where x is less than or equal to 1. 1 squared minus 1 equals 0. So the limit as x approaches 1 of f of x equals 0, which also equals f of 1. So therefore it's continuous.